Hello again. We're going to be continuing with chapter 1, and next we're going to be looking at how to draw 3D sketches of molecules. So I can go ahead and share my screen, which is our lecture notes. We are continuing on page 7 of our lecture notes, and we already talked about how to determine the hybridization of a given atom. And now we're going to look at how we can translate that into a 3D sketch of an entire molecule. So let's look at 3 molecules to start here. And I'm going to show you some models first, and then we'll see how we can translate those to the page. So here we have 2 CH3 groups singly bonded to one another. So we have a CH3 and a CH3. Let's think about what would the hybridization be for each of those atoms. So we can think about that first and then see what that model looks like. To determine the hybridization, we see how many total regions of electron density are around each. So this has 3 hydrogen atoms, and so that plus a carbon atom. So each of these has 4 regions of electron density around it, which means that it's going to be, it's going to be sp3 hybridized. And in fact, both of these are going to be sp3 hybridized. sp3 hybridization with 3 regions around tell us that we're expecting a tetrahedral geometry, In fact, that's this molecule right here is a tetrahedral geometry. The next one, each of these carbons has just 2 hydrogen atoms, and then the other carbon that it's attached to. So with 3 regions of electron density, we expect it to undergo sp2 hybridization. And then the last one with the triple bond has just the triple bond, the CH bond over here and a CC triple bond over here. And with 2 regions of electron density, we expect sp hybridization. So let's look at some models of these. SP means that we have a linear geometry. I want to show you some models of these, and then we can nope, I went to the wrong thing. Where is my camera? There it is. Looks like a camera. All right, let's see if I can show some models here of what these geometries look like so that we can sketch them on paper. So this is what a tetrahedral carbon looks like. Okay, and so this is a molecule with 2 CH3 groups. This molecule is called ethane, and you'll see that when we draw a tetrahedral carbon, only two of these bonds, the CH bond and the CC bond, sigma bond, can be in the plane. The other 2, this one is sticking out towards us, and this one is behind. Notice it's actually exactly behind this one. They're eclipsing each other, right? So what we do is we would kind of tilt it just a little bit so we could see both the front CH and the back CH. And we have the same thing over here. Now you can rotate around a carbon-carbon single bond. So if I rotated it just a little bit, I could get to a shape where now these 3 bonds are in the plane. And now we have this one sticking out and this one sticking out. So there's a couple different shapes, a couple different 3D structures we could draw for this molecule. This is one drawing, and I should note here that the bonds that are in gray, these sigma bonds, these are hybrid orbitals that are overlapping. So this is an sp3 orbital overlapping with another sp3 orbital, and that's how we make this sigma bond right here. We use Darling model kits. These are nice and easy structures, bonding kits we can use to show the same thing a lot more simply. And if we just leave these bonds open, they represent hydrogen atoms. So this represents the same thing. This is a CH3, this is a CH3. And again, if we had this conformation, this shape, these 3 bonds would be in the plane. So we would draw those as straight lines. But then for this CH2, one is sticking out towards us and this other one is behind. See that? And over here, this hydrogen is sticking out towards us and this one is behind. So we're going to have our drawing that represents that. Okay, now what does it look like when we have a double bond? When we have a double bond, this is a really cool model that shows what a pi bond looks like. Okay, remember it's two p orbitals that are overlapping. This isn't quite flat here. So this blue and green represents one p orbital. This blue and green represents another p orbital. And then when they overlap, that's what a pi bond looks like. So we have a cloud of electron density above and below the plane of the molecule. The molecule itself is in black here. So in black, we have our trigonal planar arrangement. These three sigma bonds are trigonal planar. This Darling model kind of doesn't show the p orbitals for the pi bond. It just shows these as a double bond. But you can see that there's a totally planar molecule. You have trigonal planar over here, trigonal planar over here. It's a flat molecule. Okay, another thing we can notice with these Darling models is you can't rotate now. You can't rotate because if I tried to rotate, that would cause this pi bond to break. It would cause this pi bond to break. So it's a planar molecule. So we can either have, if we drew it like this, where we could see the p orbitals very nicely. This is a wedge coming out towards us. And back here is a dash going away from us, a bond that's behind the plane of the page. Or if we were to view the molecule like this, then the p orbital now is the thing that's sticking out towards us and going behind. So there's a couple different ways you could view this. I do have a model with the another model to show the p orbitals, which you know, so this is one p orbital, kind of that dumbbell shape you can imagine. This is the other p orbital, and overlapping of those is how we make a pi bond. So there's the double bond, the pi bond, cloud of electron density above and below. There's the sigma bond directly between the two carbon nuclei. And then the other sigma bonds, again, this one's coming towards us. This is close to the camera. This is close to the camera. These are behind. These are behind. So that's one way you can draw the carbon-carbon double bond, or you could draw it like this, where it's totally planar, right? All the bonds are in the plane, all the atoms are in the plane, but then that means our pi bond is sticking out and back. Okay, so let's see if we could draw those two, and then we'll look at the triple bond, because the triple bond gets a little crazier. Okay, so let's do those sketches. So sp3 means tetrahedral. So I'm going to draw this first carbon tetrahedral. The bond angle for tetrahedral carbon is for sp3 is 109.5. Now I don't know how to draw 109.5, but I know what 90 looks like, right? And it's not 90, it should be wider than a right angle. So as long as you draw it a little wider, oh, sorry, that's not a carbon up there, that's a hydrogen. That would be a good representation of tetrahedral, 109.5. Okay, now how do we draw these other two bonds that are in the tetrahedron? Neither of these are in the plane. One is projecting out towards us. That's what we're going to draw as a wedged bond. Okay, notice that we're going to color that in. We're not going to draw it like this. That has no meaning. That has no meaning. We always, there's no such thing as a triangle. It's just a solid wedged bond. That means it's projecting out towards the viewer. And the one that's behind the page, we draw as a dashed bond, because that is, it's kind of broken because it's invisible. It would be invisible if the page is opaque. So it's behind the page, pointing away from us. Okay, and then on the other carbon, we have the same thing. We have a tetrahedral carbon. So we have one bond that we've shown in the plane. Where is the other bond in the plane? We could either draw it up here to be 109.5, or we could draw it down here to be 109.5. Either one of those is fine. Either one of those is fine. We could draw it up this way. Those would just be the two different shapes, the two different conformations that are possible. But if I draw the two bonds that are in the plane up here, then this is the region where the other two bonds are. So one is a wedge and one is a dash. It really helps to look at this at the same time as the model. Sorry, I'm not able to do that without my camera. And remember that there's free rotation here, so that's why we can get more than one 3D sketch. Many drawings are possible. Okay, now for the sp2, remember this is the molecule that is totally planar. So trigonal planar means that we should have even spacing. That's a little off. Even spacing, this should be 120, this should be 120, this should be 120. So it's always good to work with a pencil or something that could be erased so that if you draw an angle that's not quite right, you can adjust it. And then the other carbon is also sp2, which is also trigonal planar. So something like that. It's a completely planar molecule. Okay, but remember, every sp2 hybridized atom also has a p orbital, an unhybridized p orbital. So if I draw the molecule planar, then the p orbital is on the z-axis. So the one way we could draw that is we could draw one lobe wedged like it's sticking out towards us and the other dashed because it's behind the page. And we could draw another one with the same orientation on the next carbon. And then if we just kind of show them overlapping, that's how we can maybe draw that picture that we had with the foam balls or with the pink and purple orbitals. Okay, or we could tilt the molecule the other way so that we can very nicely see the p orbitals. We're viewing it from the side, so the pi bond is really easy to draw. But if we view it that way, now the hydrogen atoms are not in the plane. So one is out and one is back. One is out and one is back. So hopefully you can see how these are two points of view, two different points of view for the same molecule. And again, note that there is no rotation around a double bond because that would disrupt the aligned p orbitals. The p orbitals have to stay connected to form the pi bond. Okay, so let's jump back. Let's jump back to this camera so we could see those p orbitals again very nicely to look at those 2 points of view we had. Those 2 points of view we had. So this is the one where the atoms are in the plane, but now the purple half of the p orbitals are sticking out towards us and the pink ones are behind. Or we're viewing it this way where you could see the p orbitals very nicely, but now these two CHs are wedges because they're coming out towards us, and these two CHs are dashes because they're going away. So that's the double bond. So what does the triple bond look like? The triple bond, oh my, this is where life gets interesting. For the Darling model kit, it's very easy because it's just one piece to represent, this is the carbon-carbon triple bond. And then you could just attach one thing on either end. Right, remember carbon having 4 bonds, there's only room for one more thing on each end. So this shows that linear relationship. This is what it looks like when you're also viewing the p orbitals. So in gray here, we have our sigma bonds. That's what we're doing with our hybrid orbitals. So this is the sp and the sp. One is overlapping with the hydrogen atom s orbital. The other is overlapping with the carbon's sp. There's our linear arrangement. Okay, and now when you're sp, there's 2 p orbitals that are unhybridized. And now this time I drew one p orbital all in purple and the other p orbital all in pink. So here's one p orbital, here's the other p orbital. So that's how we're able to form 2 pi bonds. We have one set of p orbitals, the py's in this case, right? If the hybridization or in the bonding is occurring along the x-axis, here are the py orbitals that are forming one pi bond. Here are the pz orbitals in purple that are forming the other pi bond. Okay, so this is what we need to draw. So you can see that a triple bond has like a cylinder of electrons, pi electrons, all around that. And so that's why this is just a real simple way to represent that unit where we can attach one thing on either end, like we've done with hydrogen atoms here. Okay, so let's see how we can sketch this. The key to sketching this and not making a complete mess of everything is to draw it nice and big so that we have room to show all the detail, because we have 6 electrons we need to show that are being shared between those 2 carbon atoms. So it is a totally linear molecule. That's not too linear here. So a straight line. So the CH bond and the CC bond are 180 to each other. Okay, and so those are our sigma bonds. And then to draw the pi bonds, we could draw the py very easily and connect those. And then because I have some colored markers here, I can use that. The PZ is sticking straight out and back and straight out and back, showing that they're aligned. And then we can connect the PZ front and back. And that's how we could show 2 pi bonds. Remember, there's the triple bond can be described as 2 pi bonds and 1 sigma bond. Here's our sigma bond. And here, and there are 2 pi bonds. So that's a triple bond. So skill builders 7 and 8 give you some practice in predicting hybridization and geometry. Hybridization and geometry. We can kind of point out a couple bond angles again while we're here. The bonds that are in the plane, this is our 109.5. This is our 120. We could see that in a couple different places. And this is our 180. Between those two, I can't really sneak in there without making a complete mess. I think I'll just erase that whole thing so we don't have that. It's just 180. Uh-oh, I erased too much, sorry. 180 is the bond angle between the sigma bonds. Okay, so let's bring this all together to make a more complicated molecule. I think I left off a hydrogen atom here, sorry. What about this molecule? We saw this when we went to predict its hybridization. So remember what we did here, we made sure that every atom had a filled, had a complete Lewis structure. The way we do that is we fill the octets. So make sure we add in the lone pairs before we start counting regions and assigning hybridization. Okay, so we said that the nitrogen and the carbon, these are both sp hybridized. This carbon is sp2, the oxygen is sp2, and this carbon is sp3. Okay, so about each atom, we need to have the proper geometry. Okay, so we could start with that middle carbon. That middle carbon here is sp2. sp2 means it is trigonal planar. Trigonal planar, so we could draw 3 bonds that are 120 degrees from each other. 3 bonds that are 120 degrees from each other. We have an oxygen and 2 carbons. Okay, what else does it have on it? It also has a pi bond. It has a double bond between the carbon and the oxygen. So we could draw the oxygen up here is also sp2 hybridized. And in this case, it's just the lone pairs that are arranged in a trigonal planar relationship. So to show it their geometry, maybe we could just draw them as straight lines there. Okay, and how would we draw a p orbital? A p orbital then is going to be, I'm sorry, how do we draw a pi bond? The pi bond is made by adjacent aligned p orbitals. So once again, I'm going to draw them in the y and the z axis, sticking straight out and straight back, because the goal here is I want to put as many atoms in the plane as possible. So I'm sorry, I skipped our steps here. We completed the Lewis structure. We assigned the hybridization. And when you sketch it, you want to make sure you're drawing it as flat as possible with as many atoms in the page as possible, so you don't have parts of the molecule floating out in space. Okay, so so then our p orbitals and our pi bonds are going to typically be pushed to be in the z-axis. Okay, so how do we draw this next atom? Now let's move over here to be tetrahedral. So how do we draw a tetrahedral? There's going to be 2 bonds that are in the plane. Only 2 bonds are in the plane. So we could draw the hydrogen here, again, to be a little wider than 90, or we could draw it down here to be wider than 90. Your choice. They're both good. There's no right answer here. They're both good because we can rotate around that bond and get to either of those drawings. But if I draw the hydrogen down here, remember, make sure this is not 90. This should be a little wider than 90. Then in this direction is where we have the 2 other hydrogens. One is a wedge and one is a dash. Doesn't matter which is which. And you want to make sure that you draw these close to each other, because remember, they are actually eclipsing each other. One is exactly behind the other. So what we're doing is twisting it just a little bit so we could see both. So draw them fairly close to each other. Okay, and then how do we draw the triple bond? Remember, this is sp, so it's going to be linear. So if this bond is coming in this direction, the next bond also has to be going in that direction. That's what linear means. Linear does not mean horizontal. Linear means 180 degrees between the two bonds. So because I already oriented the first bond that way, the second bond has to come here. Sorry, that's not a carbon, it's a nitrogen. This is a CN triple bond. And then again, you could just draw the lone pair coming out like this. And now we have to draw 2 pi bonds. So 2 pi bonds. One of them is going to be, if this was the PY, sorry, if this is the PX, then one is going to be the Y. Make sure they're perpendicular to each other. So there's one triple bond. And where's the other triple bond? The PZ, sticking out, sticking back. Sticking out and sticking back. Okay, and when you end up sketching the molecule, if you were to build a molecule, I have it built somewhere here. Okay, if you were to build a molecule, you'll see that it actually has very similar shape. A very similar shape. Here's our camera again. So there's the way I drew it, and I drew it so that this hydrogen was in the plane, which means here's my wedge and my dash. See how they're up here in this direction? And then because this bond was coming here, then my triple bond was coming in the same direction. In this case, this is a nitrogen and this is a lone pair, not a hydrogen here. But you see it has the same shape. You can kind of lay it down and it should be representing the same shape. So we're going to have a homework assignment where I'm asking you to do 3D sketches. So it's good practice in drawing Lewis structures. And then it's good practice in assigning hybridization and drawing those sketches. So that'll give you some additional practice. The textbook doesn't have too many of these things. Okay, and the only thing that's left in chapter 1 is to talk a little bit about physical properties like, like boiling point and solubility. Just a reminder too, on that last page, second to last page, the very last page is an outline, is a summary of the entire chapter. But on that second to last page, I have some pictures of the models that I brought into the lecture of what it means to be tetrahedral, what it means to be tetrahedral, and we have a one bond that's coming out that we'd represent as a wedge, and one bond that's going back, which we represent as a dash. So that's what a tetrahedral molecule looks like. This is a space filling model. It's kind of interesting, showing the volume taken up by the electrons. Okay, triple bond has 2 p orbitals, 2 sets of p orbitals making 1 pi bond, and then a second pi bond. And then it's the hybrid orbitals that make the sigma bonds. The hybrid orbitals, the sp orbitals that make the sigma bonds. And then the double bond we can make for trigonal planar. That's the sp2 hybridization, and we can orient that either way, where all the sigma bonds are in the plane, which forces the p orbitals to the z-axis, or the p orbitals are in the y-axis, which makes the CH bonds both wedges and dashes. Both wedges and dashes. So we're either looking at that molecule flat or from the side. All right, so good luck with those 3D sketches, and we will finish up the rest of chapter 1 and our review of general chemistry and our final lecture.